This video is about selective amplifiers. They are the heart of an oscillator, and the purpose is to find out what are the limitations for different kinds of selective amplifiers. Here I have 4 bipolar transistors in parallel. MPSH10 is the type. There are 2 crystals in parallel. I will change that later. The input is a transformer to transform from 50 ohms down to maybe 10 ohms or 5 ohms, I don't remember. But there is a resistor here of 3 ohms to set the impedance at this point. The impedance at the input of the transistors, the crystals, go to the emitter here, and the base is decoupled to ground, but with some ferrite pearls, because these transistors tend to oscillate on 500 megahertz or somewhere. The output has a transformer here. Note there is a lot of copper parallel to the wires. That's to increase the coupling between the primary and the secondary. And then there is a resistor to set the impedance to 50 ohms, so measurements will be correct. The test system is this low noise amplifier. It has a 15 megahertz low pass filter on the input to prevent peculiar results in the event that some amplifier is oscillating on high frequency VHF. That could cause false readings of too good noise floors. And at this first time I have a 50 ohm dummy load connected to this amplifier, and then I set the S meter to read close to 0 dB. That's how I calibrate. I have now put the screen on the box, and I have a 50 ohm dummy load on the input. This is what I see at 10 megahertz. It's the noise around 10 megahertz, because at that frequency there is a low impedance on the emitter, so the transistors give gain. But well away from this frequency, the impedance on the emitter is very high. And I will look at the noise floor, let's say 50 kilohertz from the frequency. And now the current is 8 milliamps, and the noise floor is 0.8 dB. Now the current is 16 milliamps. I changed the emitter resistor, and then the noise is higher, and there is a bug in Linrad which sometimes makes the noise readout not work. But now the noise is 3 dB. That's the noise increment compared to a 50 ohm resistor. And I write these things on a paper, 8 milliamps, 16 milliamps, and I will continue with other current levels. I have disconnected 2 of the transistors. The emitter and the base are now in floating, so only the collector is connected, so they don't contribute to the performance of this thing. The screen is back, and the current is now 8 milliamps, and the noise floor is 0.82. That is for 2 transistors, 0.82. Well, I didn't take the decimal last time, but as you can see, it's the same value. It seems the number of transistors doesn't matter, it's only the total current. But note, what you see here is the total current to the amplifier, not through the transistor. there is a voltage divider for the base that takes some current also. But anyway, this shows that using 4 or 2 in parallel does not affect the noise properties. Now I'm using just a single transistor. I happen to destroy 2 of the ones. With just one transistor I see a little bit higher noise levels. Not much, but it's significant, and it's the same on all the different current settings. Now I have 8 transistors in parallel. That could provide enough output power, and probably it wouldn't change the noise properties at all. So what I find is the noise increases when the current increases, but the number of parallel transistors does not matter much. Having just a single transistor is a little bit less good than having several. But going from 2 to 4 to 8 makes a very small difference. More transistors in parallel means I can take out a lower impedance on the collector side and get more power out from this amplifier. But of course with more power through the crystal. Now I have only one crystal but 8 transistors in parallel. The current is set to 32 milliamps, which means the current is with a big margin large enough to handle the power that is delivered through the crystal. This is what I see in the network analyzer. That's with the power level of minus 20 dBm. I change that to 0 dBm. And you can see the curve is not properly shaped anymore, and it's a little bit lower. It means I am overheating the crystal. So since this network analyzer is not properly working, I cannot set the power level in steps of 1 dB. I have to insert an attenuator. So I add now 2 dB of attenuation, like that, and then go for minus 20 dB here on the power, and there is still a difference, so I go down another 2 dB and then put the full power. And now the difference is very small. I reduce by just 1 more dB. And then go down minus 20. And the difference is probably less than 1 dB. So I attenuate by 1 dB. And then again bring the power up. And now the curve is very similar. So this seems to be roughly the maximum level for this crystal. And to be conservative, I just reduce 1 more dB like this. And then look at it again. Minus 20. And now the difference is very small. The selectivity is very nearly the same. Just the level is a little bit lower. We put now a current probe on the crystal. That doesn't change what I see on the network analyzer. But on the oscilloscope I see like this. The peak current is about 17 milliamps, because 1 millivolt is 1 milliamp. The power is modest. I don't need as much current as I have. It's running at 32 milliamps, and I turn the current down until I see some difference. Well, I do see a small difference already here. So actually I need these 30 milliamps for this input power level. Now I'm running the maximum permitted current through the crystal. And I'm looking at the output. This is a fixed frequency from here. And the level is plus 13 dBm. This has to be compared to the noise floor I established previously. The noise floor as 36 milliamps. The noise figure is 5 dB, which means minus 169 dBm per hertz. And I see a 5.5 dB increase at this level of current, roughly. And that is 3.6 times. Means that the noise is 2.6 times above minus 169. 2.6 times is 4 dB, so I find that the noise floor is at minus 165, and the signal, the carrier, is plus 13, so the limit for this design is I cannot reach better than minus 178 dBc per hertz. That is while keeping the Q of the crystal at its full value. I could drive it harder to get a better wide range noise floor, but that would be at the expense of a degraded close range noise, sideband noise from this intended oscillator. There is a more convenient way of measuring the noise floor from this amplifier. I'm using this noise head. I have set it to 5.6 dB, and it has been running for a while, and I'll switch it off. And then I look at the change of the noise floor. It goes from 3.0 to very close to 0. So the noise figure wasn't 5 dB, it was 5.6. And for 32 milliamps I want 5.5 dB. So I turn on the current on the noise head until I read 5.5 dB. And then I see a noise figure of 9.6. So the noise floor is simply minus 174 plus 9.6. That gives me 164.4 dBm per hertz. I computed 165 before, but that was assuming the noise figure of this system is 5 dB, but it wasn't, it was 5.6 as you have seen. There are two crystals in parallel now, and the power is quite a bit too high, and I see that by turning it down and look at how the curve changes. And you can see it becomes symmetric now and much higher. So I turn down the signal level by something, let's say 3 dB, and then go up with the power again. And this is still too much. 2 dB more attenuation. And then minus 20. And still too much signal, it seems. Now I have lost less than 1 dB, and the shape of the curve is very similar, so this is maybe the level I can use. Looking at the current through the two crystals, I find not very surprising that this is just exactly twice as much as I had for a single crystal. So I have twice as much power into the transistors. And the current through the transistors is 60 milliamps, 59. And I turn the current down while looking here. And this is not enough. I lost a little, but this is half the current, 32 milliamps, so should be okay, maybe something like this. So I have set it to 45, 46 milliamps. Now the transformer, output transformer here, is designed for a single crystal. So on the output I am now loading with not only the network analyzer but also with a 50 ohm dummy load in parallel. So I am loading it with 25 ohms now. Now I've set a fixed frequency, 10 megahertz, and a signal level that gives me the crystal current that I have decided to be the maximum I want to run through these crystals. And then the spectrum analyzer shows me 15.5 dBm. But the real power is twice as high because I have this dummy load here that takes half the power. So the useful power with the properly optimized transformer would be 18.5 dBm. With the screen back in place, this is what I see on the linear screen. It's 5.8 dB at 46 milliamps. To see the same 5.8 with the noise head here, I have to set it to 10.5 dB as a noise figure. Now this noise floor that I see, that is when loading with 50 ohms. When I change the transformer for 3 dB less gain and matched to 50 ohms, this will become 3 dB better. So it's minus 166.5 to compare with 18.5. With one crystal I got 178. With two crystals I see minus 185 dBc per hertz. I cannot claim I understand exactly what happens, but it looks like I have gained 6 dB. Actually the numbers give 7, but then intuition tells me it's a doubling of the number of crystals will give 6 dB. So it takes a lot of crystals to reach the level I have of the vacuum tube oscillator. But on the other hand, there I'm driving the crystals very much harder, so the close range noise is no good. I would like to reach minus 200 dBc per hertz, so I guess 16 crystals would be enough for that. But the transistor current would have to be half an ampere, and the voltage is 25 volts. And the transistors are rated 350 milliwatts. So if I give them 300 milliwatts each and neglect the power in emitter resistors and other places, I need 40 transistors. So it is possible, and maybe it will work like this. Maybe it will not, because there will be flicker noise because of the transistors. Maybe that's only in the close range, I don't know. And I will look at that maybe, unless I find that some other architecture looks more promising than this. An additional remark: putting many transistors straight in parallel is not necessarily a good idea. Suddenly some of them failed when I was running at the full current I can have. So to prevent that from happening, I have put a 68 ohm resistor in each emitter and in parallel with 0.1 microfarads. That's these blue capacitors, and you can't see the resistor, I think. Well, so having many more than 8 transistors will look pretty ugly, I think.